On the off chance that neutrons are disappearing, what if they're vanishing into an alternate universe? It might sound outlandish, but this is a legitimate area of scientific exploration that researchers are currently testing. Imagine a world where parallel realities aren't confined to fiction but are instead a tangible possibility. What if we could jump between different dimensions as easily as hopping on a train to travel from one place to another? Could each decision we make create an entirely new universe where we exist as a different version of ourselves? This concept of alternate realities may not be as fictional as we once thought, and recent findings from CERN, the European Organization for Nuclear Research, have sparked intriguing possibilities about the existence of portals to other dimensions. But what does this mean for us? Is it even feasible? And what are the potential consequences of interfering with the fabric of existence itself? To understand CERN's groundbreaking research, particularly regarding portals, dimensions, and particles, we first need to explore what CERN is and how it operates. Established in the 1950s, CERN is located in the picturesque region straddling the French-Swiss border in Europe. It was founded by representatives from 12 European countries with one goal: to create a hub for nuclear research that would position Europe at the forefront of scientific discovery. Over the years, CERN has contributed tremendously to the world of science, most notably with the creation of the World Wide Web in 1989 and the construction of the Large Hadron Collider (LHC) in 2008. The LHC, still the world's most powerful particle accelerator, is buried deep beneath the Earth's surface, spanning more than 17 miles in circumference. The LHC was designed to explore the very core of matter, giving us insights into the fundamental particles of the universe. The LHC's core objective is to help us understand the universe on a deeper level by smashing particles together at incredibly high energies and observing the results. In doing so, it uncovers new phenomena, including the potential existence of other dimensions. But why conduct these particle collisions in the first place? What do we hope to uncover by crashing particles into each other at near-light speeds? The answer lies in the pursuit of knowledge. We are trying to answer fundamental questions in physics. For instance, where are the new families of particles predicted by supersymmetry? What happens when particles collide at various speeds? Could there be unknown particles out there that we have never detected before? These questions form the foundation of CERN's particle physics research, pushing us closer to the truth about the universe's building blocks. One of the most intriguing aspects of CERN's work is its exploration of particle collisions. These collisions provide scientists with a direct way to study the fundamental pieces of the universe. By using powerful accelerators like the LHC, researchers can speed particles to nearly the speed of light, providing a unique opportunity to observe their behavior and interactions at unprecedented levels. The LHC accelerates particles through a series of steps. Initially, particles are injected into a linear accelerator, LINAC, where they are charged and accelerated to speeds of up to 50 million electron volts, MeV. From there, the particles are fed into circular accelerators, such as the proton synchrotron, PS, and the superproton synchrotron, SPS, where their energy is increased to trillions of electron volts, TeV. Eventually, they are fired at one another in head-on collisions within the main LHC ring, which spans 27 kilometers, 17 miles, in circumference. These high-energy collisions result in the creation of a variety of particles, some of which have never been observed before. This wealth of data is recorded by detectors positioned around the collision points. These detectors track the particles' movements, measure their energies, and determine their types. By studying the collision patterns, researchers can learn more about the properties of the particles and gain deeper insights into the universe's fundamental nature. One question that often arises is how the particles in the LHC can avoid missing each other during these high-speed collisions. The answer lies in the way the particles are organized. Rather than being randomly scattered, the particles are bundled into tightly focused beams. Each beam contains roughly 100 billion protons, and the collisions happen in quick succession, sometimes reaching billions per day. Despite the excitement surrounding the LHC and its discoveries, there have been concerns about the potential risks associated with such high-energy particle collisions. Some early fears, for instance, revolved around the possibility of the LHC creating a black hole that could consume the entire planet. However, these concerns have been largely dismissed by scientists, who have concluded that such events are extremely unlikely. Despite these concerns, the discoveries made by the LHC continue to propel us forward in our understanding of the universe. The recent exploration of alternate dimensions, linked to the study of particles, is just one example of how CERN's experiments are opening up new and exciting possibilities in physics. As research continues, we may be on the brink of uncovering answers to some of the most profound questions about the nature of reality itself, including the possibility of parallel universes, portals to other dimensions, and the fundamental structure of our existence. In conclusion, the work being done at CERN is not just about smashing particles together. It's about uncovering the very fabric of reality. From the quest to find new particles to the exploration of alternate dimensions, CERN is pushing the boundaries of science and opening the door to extraordinary discoveries that could change our understanding of the universe forever. In 2022, physicists made a startling recognition of a mysterious early-stage molecule known as the X molecule, specifically X3872. This molecule was first discovered in 2003 by Japan's Riken experiment, which involved a particle collider that smashed high-energy electrons and positrons together, creating the enigmatic X molecule. However, the molecule decayed too quickly for detailed study. It was then suggested that X3872 could be better understood in the context of quark-gluon plasma. By 2022, over 100 of these X particles were identified within quark-gluon plasma, formed by colliding lead particles. These particles were found to exist briefly after the Big Bang, and the discovery was published in Physical Review Letters on January 19. Did you know that what we can see in space, like planets, stars, and galaxies, only makes up a tiny fraction of the universe, about 4%? The vast majority of the universe is invisible to us, comprising mysterious substances that don't emit light or any other form of detectable radiation. These substances, which scientists call dark matter and dark energy, are inferred through their gravitational effects on stars and galaxies. While we don't fully understand what they are, their existence presents fascinating possibilities for future discoveries. Dark matter alone makes up approximately 23% of the universe. Its existence was first hypothesized in 1933 when scientists noticed that galaxy motion suggested more mass than could be seen. Though we can't observe or interact with dark matter directly, we study it by analyzing its gravitational effects, similar to how one might investigate a crime scene by examining footprints left by a criminal. Scientists are exploring the possibility that dark matter may consist of supersymmetric particles, which are theoretical counterparts to the known particles in our universe. Ongoing experiments, such as those at the Large Hadron Collider, are searching for these elusive particles. Now, let's turn to dark energy, which constitutes about 73% of the universe. Dark energy is believed to be responsible for an astonishing discovery in the 1990s. The universe's expansion is accelerating. This observation contradicted the previous assumption that gravity would gradually slow down the expansion over time. Instead, something seems to be pushing the universe apart, and scientists have named this force dark energy. Some believe dark energy is linked to a concept introduced by Einstein, the cosmological constant. One way researchers study dark energy is by looking at how galaxies are distributed across the universe. By analyzing the light from supernovae, exploding stars that are bright enough to be seen from vast distances, they can track how the universe has been expanding over time. Another hypothesis is that dark energy might be a new form of energy field that fills all of space. Although we are far from fully understanding dark energy, studying it could help answer one of the universe's greatest mysteries. Will the universe continue expanding forever, or will it eventually stop? Enter CERN, the European Organization for Nuclear Research, which has been observing strange behavior in neutrons, one of the building blocks of atoms. In certain experiments, neutrons appear to disappear and reappear, almost as if by magic. Some scientists believe that these neutrons may be slipping into a parallel universe. This theory suggests that our universe might be just one of many, like bubbles in a cosmic bubble bath. If this theory is correct, there could be other dimensions out there that we cannot perceive. CERN is now designing experiments to test this hypothesis, creating conditions where neutrons might escape into another dimension. If successful, this would mark a monumental leap in our understanding of the universe, potentially allowing us to explore parallel worlds and uncover new particles, forces of nature, and even novel ways to travel through spacetime. CERN's work holds the potential to radically alter our understanding of dark matter, dark energy, and the very fabric of reality itself. This research could revolutionize everything from quantum computing to energy generation. By delving into the underlying nature of spacetime, CERN not only seeks to unravel the mysteries of dark matter and dark energy, but also aims to reveal new laws of physics that could lead to groundbreaking advancements in technology. Furthermore, the study of parallel universes raises profound philosophical questions. If other dimensions exist, with different physical constants, what does that mean for our understanding of reality? Could our universe be just one variation among countless possibilities? These are not merely academic questions. They challenge the very foundations of how we perceive existence and could reshape entire fields of philosophy and theology. The technological implications of such discoveries are staggering. From developing new materials with properties we can't yet imagine to harnessing vast sources of energy from alternate dimensions, the practical applications could be endless. As CERN continues its pioneering research, we are on the brink of a new era in scientific exploration. The answers it uncovers could completely transform our understanding of the universe and open up new realms of possibility for humanity, reshaping our future in ways we can only begin to comprehend.